Welcome to the part E of chapter 4, E111 lecture series video. We're almost through chapter 4 now. And in this video, we're going to be transitioning from what we had talked about for the past few videos on node voltage and mesh current techniques. We're going to be moving into some techniques where we start to consider cases where we don't necessarily want to solve for an entire circuit. We're going to sort of learn some tricks that we can do if we're only interested in one particular quantity in a circuit or one particular region of a circuit, and ways that we can simplify a circuit or reduce the complexity of the problem that we need to solve. But before we get there, let's say goodbye to node voltage and mesh current with probably the topic that students ask the most once we get done, and that is, how do I know which one to pick? Node voltage and mesh current, they're both complementary techniques. They're both very useful techniques. They're both techniques that are widely implemented not only in human analysis, but also in system analysis and in computer analysis of these systems. So how do we pick one, right? Ultimately, if we have a choice, if we're doing something by hand, they're both useful, but when is one more useful than the other? Well, I think I said in a video a while back that about 70% of the time people choose the node voltage technique. And that's kind of grown. It used to be they only taught the mesh current technique. The mesh current technique was kind of the only one that was formally introduced. Node voltage was node voltage is still kind of a strange approach. Not strange, but the whole pick a reference node, set it as 0, solve everything relative to that 0. It's a little bit different. I mean, it's a slightly more unorthodox way of analyzing circuits than what was done in the past. In the past, it was just meshes, and meshes are still, on a system side, a more popular way to solve. But people like the node voltage. I like the node voltage. And the biggest reason is, quite often, that node voltage, being able to set one of your nodes to 0 and subtract out one of those unknown nodes, quite often that means that you're going to have fewer equations to solve if you use the node voltage technique versus the mesh current. But that's not always the case. So how do we prioritize? How do we choose if it's up to us? And it won't always be up to you. If you're taking a quiz or a test, quite often it will say, use this technique. And the reason it'll say that is because we need to make sure, teaching the class, that you've mastered these different techniques. So we need you to demonstrate to us your proficiency in all of them. But if it is up to you, then what do you do? Well, so I have a handy, ultimately it's up to you, whatever you're most comfortable with. But I have a sort of handy listing of things that I go through when I'm picking between the two. And the biggest one for me is the number of equations, no doubt. The number of equations. The difference between, if you can solve one equation with one unknown instead of 2, almost always that's going to be easier. If you can solve 2 instead of 3, awesome. If you can solve 3 instead of 4, now you're getting to the point where solving 3 systems of equations instead of 4, that's potentially the difference between having to switch to a tool like a linear algebra or matrix analysis. You can potentially save yourself from having to do that by using one technique versus another. So number of equations, fewest equations is definitely the most important consideration for picking between the two. The other one is, are there any shortcuts? So looking at the circuit, are there any, if you use node voltage, could you use a super node? If you use mesh current, could you use a super mesh technique? Are they basically saying, not just looking at the raw equations, but is there a way we can kind of make 2 of those equations sort of one equation instead? And also, what are we ultimately solving for? So your choice of node voltage or mesh current might boil down to, if everything's kind of equal and you're trying to solve for something that's easy to find if you know the currents, then maybe go mesh current. Or if you're trying to solve for something that's easy to find if you know the voltages, then maybe go with node voltage in that case. So let's look at this example circuit here. It's fairly simple circuit. What if our question is, find the power dissipated by this 2 amp current supply? So which technique might we want to use here? Well, let's go through this analysis. If we wanted to do node voltage here, how many equations would we have to solve? Well, we have 2 essential nodes in this circuit. So by node voltage, that's 2 minus 1. That's going to be 1 equation. Okay. If there's mesh current, we have 2 essential meshes. Okay, so right there, node voltage kind of wins out, and probably that would be enough for me to just say, let's just do a node voltage analysis. But let's keep looking at this circuit. Are there any shortcuts? There is. We could do a super mesh if we wanted to. So we do have a current supply between here. So, you know, really, if we did do mesh current, we could basically write it as one equation. Maybe it's not too bad. You know, that's a point in favor of mesh current here. And then are we solving for a voltage or current? Well, the problem at hand is I said, what's the power for this 2 amp supply? How do you find the power for a current supply? You have to solve for the voltage across it. So this is a case where node voltage would be much more handy, because if we do node voltage, we're going to know, you know, if we make this our reference, and we do node voltage, we're going to be solving for this voltage here. You know, whatever, VA or V1 or... And if we know that voltage, we know the power for the current supply immediately. We know the current through the current supply, we know the voltage across it, that's it. If we had solved for the mesh currents, if we had solved for the mesh currents instead, then finding this voltage across this current supply would mean we'd have to do a Kirchhoff's voltage law equation around the loop and solve for this unknown. So we basically have to solve for this voltage, using the current, and we know this voltage, and we have to, you know, KVL would tell us the voltage on the other one. That's a pain. So all of these things to me for this circuit are points in favor of using the node voltage technique. I would probably use node voltage on this. Let's look at this circuit. So node voltage or mesh current here? Well, let's look at the equation. So we're going to do a table. Node voltage, mesh current. So how many equations? Well, for node voltage, we got 1, 2, 3, 4. We got 4 minus 1. That's going to be 3 equations. What about mesh current? Mesh current, we got 1, 2, 3, but woo, look at that one. So mesh current, we have 3 equations, but really we have 2 because one of those mesh currents is already solved. So mesh current, we got sort of 2 asterisk, right? Because we have 3 meshes, but one of them is already known. So immediately, that's a big, strong point in favor of mesh current for analyzing this. I didn't say what I was solving for, but let's say we're solving for this IX here. So we're solving for this IX. Okay, so, you know, right now, winner mesh current here, just based on the equations, but let's keep going through. Are there any techniques we could use to make this a little easier? Could we do a node voltage? Or could we do a super node or super mesh? I don't see any. I don't see any super node or super mesh here. One thing to note, though, is we do have a dependent supply, which means that for this dependent supply, we need to write an expression for IX. IX could be written as this current here could be this mesh minus this mesh. So it would be this mesh minus 4 if we were using mesh current. And if we were doing node voltage, IX would have to be represented as, you know, VA minus VB divided by 4. So that's kind of not a huge selling point, right? I mean, you know, IA minus 4 versus VA minus VB over 4. I don't know. Now, you know, that's not a huge thing, but these are the things you want to consider. You want to consider these. So let's just say, you know, extra techniques. Extra bonuses. These are both of them are, we can't use node voltage, or we can't use super node, super mesh. And, you know, writing the equation for the dependent supply is there's not a huge difference. Maybe a little point in favor of mesh current. Oops. Maybe a point in favor of that. I don't know. A little bit. And then the last one is, what are we solving for? We are solving for a current here. So, you know, maybe little check mark in mesh current, but overall here, this would be a circuit where we'd probably want to do mesh current. You know, some fewer equations. We need to manipulate currents anyway, so mesh current for this one. That's the way I would analyze it. But again, you might find when you do these that there's something about it that you prefer in one, or there's one that you tend to make fewer mistakes with, or there's just one that you just like better. So ultimately, it's up to you. It's what you're comfortable with. These are tools for you to use. And unless we tell you, you must use this, then, everybody's got their own different comforts and their own different preferences, and just go with what you like. Go with what works best for you. Oh, that's our goodbye to node voltage and mesh current. That's kind of we put the cherry on top. We put the lid on it. I don't know. But node voltage and mesh current never go away. So node voltage and mesh current, these are really powerhouse techniques. You will use these throughout the curriculum in electrical engineering. We'll use these later on in this chapter, even when we do later analysis. It's all the time. It's super easy to solve. We'll want to come back to, how am I going to find this unknown? It looks like an easy mesh current, easy node voltage. Just toss it in the equation, right? So they don't go away, but our discussion of them for the purposes of teaching the technique ends here. Source transformation. So this is moving into what I said, moving away from node voltage and mesh current are these great techniques for when we want to solve everything about a circuit. We have a circuit that we don't know what the currents are, what the voltages are. We want to know everything we could possibly know about that circuit. That's where we'd use node voltage and mesh current. But there's a lot of times where you don't necessarily care about a whole circuit. Maybe you just say, I just want to know the voltage across this one resistor. That's it. Or I just want to know the power for this one voltage supply, and that's it. And you don't care about everything else. And maybe in that case, you don't want to necessarily analyze the entire circuit. You just want to find that one little parameter. And that's where the techniques that we talk about for the remainder of chapter 4 come in handy. These are not techniques that are going to be the ones you want to use if you want to solve for all the unknowns. But they are pretty handy techniques for when you're just trying to just find one little thing about a little part of the circuit. So the first way to do that is source transformation. Source transformations are a way that you can convert a source and a resistor into an equivalent of a different source. So the idea here is anytime in a circuit that you have a voltage supply in series with a resistor, it is possible to convert that into a current supply in parallel with a resistor, an equivalent current supply in parallel with a resistor. And the equation that relates to that equivalent supply is this. So if we have a voltage supply Vs in series with resistor R, we can say that is an equivalent current supply Is, where Is is Vs divided by R in parallel with the resistor R. Now this is a pretty big thing to just drop and just say, oh, we can just do this. We have voltage supply in series with the resistor. Now let's make it a current supply in parallel with a resistor. And the book goes through the proof of this. I'm going to skip the proof of this, but one quick thing, even if you don't go through the whole proof, one thing that's really useful to always do is just say, what's my short circuit, open circuit situation? So if we want to not prove this to ourselves, but just sort of maybe sanity check this, one thing I always like to do is say, let's say I put a wire between these terminals AB. What's this current flowing through here? Well, it's pretty obvious. If I put a wire between these terminals, the current's going to be Vs over R. It should be fairly obvious. And let's look at this equivalent circuit here. If I put a wire between these terminals, what's this current flow here? Well, if I put a wire between these terminals, that wire is in parallel with this resistor R, so there's going to be no current flowing through the resistor R. There's going to be no voltage across R, no current flowing through it. And that means all of this current Is is going to be flowing through my short here. So the current here is going to be Is. So if we say Is equals Vs over R, well, we at least have a little bit of a sanity check here that, okay, at least in the short, the one case we tested quickly, that is true, that the current flowing, if we short the terminals, yes, then it's pretty obvious that the current in one case will be Vs over R and the current in the other case will be Is. Let's do another quick little test. The amount of time I'm spending on this is probably longer than if I just proved it from scratch, but let's do another test that I like, and that's the open circuit voltage. Let's just say we leave these terminals open, find the voltage here. If we leave these terminals open in this case, what's the voltage going to be? Well, if we leave these terminals open, the voltage, there's going to be no current flow through this resistor, which means there's going to be no voltage drop across this resistor. So if the terminals are open, there's no current through the resistor and no voltage drop across the resistor, then all of that voltage Vs has to be dropped across these terminals. So we must have Vs volts across these terminals AB. What about in this case? What if we leave the terminals AB open? What's this voltage here? Well, we leave the terminals AB open, all of this current IS is going to flow through this resistor R. So the voltage across R is going to be VS. Oh, sorry. The voltage across R is going to be IS times R. So the voltage across AB will be the voltage across R, which will be IS times R. So we get VS equals IS times R. And rewriting that, we get IS equals VS over R. Okay, well, that's another circle here, which helps boost my confidence in the correctness of this equation. Still not a proof. The way to do the proof is to put a resistor with variable RS across the terminals AB and solve for the equivalency. Solve for under what condition these two circuits have an equivalent current flowing through that resistor for any values of RS. And that's what the book does, and it doesn't take too long, but rather than doing that, I just did these quick little checks. There's a reason I did the open circuit voltage check and the short circuit current check. Where you're going to see that later, but that's just something for me is a quick test that I like to do to sanity check myself. Now, source transformations are handy. It's often very useful to take a voltage supply in series with a resistor and convert it to a current supply in parallel with a resistor. It's handy usually because after doing that transformation, we are then able to combine that equivalent resistor with another resistor and simplify the larger system even further. But one thing to note is equivalent source transformations they result in a circuit that is equivalent to everything else. But they do modify the circuit. So when you when you take a region of a circuit and you say, here is a circuit that's equivalent to it, and you change it into its equivalent form, even though that change doesn't impact the rest of the circuit, you are overall still changing the circuit. So what that means is that you're losing information about the original circuit when you do these transformations. And so things like calculating the total power for a circuit, those don't work after you do these transformations. So you could take a big circuit that has 20 supplies and 50 resistors, and you could reduce it down to a single voltage supply and a single resistor. But if you solve for the power dissipated by that resistor, or you solve for the power generated by that supply, you can't just say, oh, that's the total power from my original circuit. You can't just say, oh, that's the total, that's the total power, delivered to or dissipated by my original circuit. You can't say that. You've destroyed that you've destroyed all that information about the original circuit. You can no longer make claims about the original circuit. The only thing you can still make claims about is the portion of your circuit that you left untouched. So source transformations only are useful for determining things about the parts of your circuit that you don't transform, oddly enough. And you'll see that show up later on here. Okay. So source transformations, let's do, in this case, find the current through the 6-volt source. So we're going to try to find this current I here. And the general technique is when you want to find some unknown in a circuit and you want to do it by simplifying a circuit with source transformations, you always want to start source transformations away from the region of the circuit of interest. So in this case, I want the current through the 6-volt supply. Well, that means that I don't want to just start transforming the 6-volt supply. The 6-volt supply is in series with a 4-ohm resistor. I could convert the 6-volt supply to a current supply in parallel with a 4-ohm resistor, but that would be really bad because then my 6-volt supply wouldn't exist and I wouldn't be able to answer questions anymore about the current through the 6-volt supply. So I'm going to leave this untouched. I'm going to leave this part of the circuit untouched, and instead I'm going to start over here. I'm going to start messing with this circuit over on the right side of the circuit rather than on the side of the circuit that's near my supply of interest. I'm going to leave this supply untouched. Okay. So let's see if I left myself. Oh, I did. I left myself another page. Great. Okay. So let's start simplifying this. And again, our ultimate goal is to find this current here. Well, first of all, is there anything we can simplify about the circuit? Do we have any resistors in series or parallel? No. If you said, yeah, the 30 is in parallel with the 20, everybody says that. Everybody says that. More commonly, people might say, oh, the 6 is in series with the 5. They're not. So the 6 is not in series with the 5. It's got the 20 here. The 20 is not in parallel with the 30 because they don't even share one terminal, right? They are visually in parallel, as in they're two parallel objects, but they are not electrically in parallel because not only do they not share two terminals, they don't share one terminal. So Nothing in this circuit is in series or in parallel, and that's what trips people up the most in this portion of it. I guarantee you on the next exam, there will be a question, at least one, on source transformations, and I guarantee you 20 to 30% of you will make a mistake of just a simple what's in series, what's in parallel. So 20 to 30% of you will say, oh, 6 plus 5 equals 11, and so we can take that out and put an 11 somewhere in there, and that's wrong. These are not in series. Right now, there is no resistor in series with another resistor in this circuit, and there's no resistor in parallel with another resistor in this circuit. But we can change that by doing source transformations. So we have a 40-volt voltage supply in series with a 5-ohm resistor. What is that equivalent to? Well, a 40, if we go back, so Vs is 40, R is 5, that's going to be equivalent to Is, where Is equals Vs over R. That's going to equal, what did I say, 40 over 5? Yeah. So this is going to be equivalent to Is equals 40 over 5 equals, it's going to be 8 amps. And that is going to be in parallel with a 5-ohm resistor. So let's redraw this circuit really quickly. There's no redrawing circuits quickly, I should say. So we can redraw that. So instead of there being a 5 in series with a 40 now there's going to be a 5 in parallel with a 8. Oops. And people, one of the other things that tends to throw students off is they get the orientation of the supply wrong. So whenever you do a transform current supply, voltage supply, the equivalent supply, the arrow of the equivalent current supply will always be pointing towards the positive terminal of the voltage supply. So in this case, we had the voltage, the positive terminal up top, so the arrow will be pointing in that direction. It'll always be pointing in the direction of that positive terminal. And the other thing is, people might say, well, why'd you put the 5 on this side of the current supply? Well, it doesn't matter. These are parallel branches. We can switch the order of the branches, right? I mean, just imagine if you had this circuit physically in 3-dimensional space, you could just crank rotate the wires around and switch the direction. It doesn't matter what order things are in parallel. It doesn't matter what order things are in series. So we can switch them around. And you'll notice, though, after we do this transformation, now we got something interesting, right? Now we got a 5 in parallel with a 20. So now we can actually reduce this. So we can say 5 in parallel with 20. That's 1 over 5 plus 1 over 20 to the negative 1. It should be 4, but let's go through it. It's 4. So we can redraw this as a 4. All right, we're well on our way. We've simplified this circuit. We're down a resistor now. Good for us. So now, do we have anything in series or parallel? Is there any more simplification we can do? Now, this is, again, people tend to get too excited about, I got a bunch of resistors, I can simplify them. No, right now, this circuit, this simplified circuit, there is nothing in series or parallel right now that we can simplify. So there's no more simplification we can do. And so what does that mean for us? Source transformation, one more time. So one thing to note is if we transform this back, if we take this 4 ohm in parallel with an 8 ohm, and we switch it back to a voltage supply in series with a resistor, then that will all be in series with everything here. So let's do that. Oops. Let's transform this back. So let's say, so now we have an 8 amp current supply in parallel with a 4 ohm resistor. In one equation, it should be intuitive, but if Is equals Vs over R, we can also say Vs equals Is times R. So to find the current supply equivalent, you take the voltage supply divided by the resistance it's in series with. To find the voltage supply equivalent, you take the current supply multiplied by the resistor it's in parallel with. So in this case, 8 times 4 equals 32 volts. So we can replace this 8 amp in parallel with a 4 with a 32 volt with a 32 volt in series with a 4. Now what can we do? Now there's a lot of stuff that we can do. So now we have the 6 and the 4 and the 32 and the 10. These are all in series. And the nice thing about things in series is we can switch their order in series and they're still equivalent. So I'm going to switch the order of these things in series, and I'm going to put the 10 up here. It's kind of ugly there. And now it's pretty obvious we got all of these in series. And now we can combine this. We can say 6 plus 4 plus 10 equals 20. Now we can replace this with a 20 ohm resistor. Okay, can we simplify anything? Once again, this is where a lot of students say, "Oh, I got a 20 in series with a 4." You don't have a 20. And the reason I always point out these mistakes is because I have graded a lot of problems in my time, thousands and thousands of exam problems, and it hurts my soul when I see students make series and parallel resistor issues, because it's so important and it's so unnecessary. But I know why it happens, right? You know, visually you see it. You see these things. They look like they're in series. They look like they're in parallel. And you want to be able to combine them, but you just can't. So in this case, once again, there's nothing in series or in parallel that we can combine right now. Not to worry, though. We can just do another source transformation. So we have a 32 in series with a 20. So a 32 volt supply in series with a 20 is equivalent to a 32 divided by 20. That's going to be a 1.6. So it's equivalent to a 1.6 amp supply in parallel with a 20. Okay. All right. Now we got a, now we can combine the 30 and the 20. So now we got 30 in parallel with a 20. If you've done enough of these homework problems, you probably know what a 30 in parallel with a 20 is. Try to guess. It's 12. So we can replace these in here. Oops. The 12. And we can do another source. You know, now at this point in time, we've simplified this circuit a lot. If my question was, what's this current here? I could probably, finding this current is very easy now with a mesh current. Okay, this would be a very quick equation with mesh current right now. It would basically be 1 because, this mesh, the current's known. We know the current in this mesh would be negative 1.6, so we could probably write this as one equation. We could solve it really quick right now. But we can do one. We can do one more. We can make the mesh current even easier by just doing one more analysis. Let's do one more transformation. So we can convert a 1.6 amp supply in parallel with a 12 ohm resistor to a 12 times 1.6 equals 19.2. So we can convert that to a 19.2 volt supply in series with a 12. And then we can combine these into a 16. And we could find this current. I mean, it's fairly easy to find this current right now because we essentially have, the current flowing in this direction is going to be the voltage across this resistor because divided by 16. And the voltage across this resistor is going to be starting at the positive one, going back down here. The voltage across this resistor is going to be 6 minus negative 19.2. So the voltage across the resistor is going to be negative 13.2 volts divided by 16. It's negative 0.825. So, I mean, we could do that, or maybe we're just not comfortable. We got these supply. We got one supply this way, and we're kind of a little. I'm worried about getting the number backwards, and I'm worried about getting a sign thing, and so we just say, all right, let's just finish it off with a mesh current. We got this current I, and luckily I is I, right? So then we just go negative 6 plus I times 16 plus 19.2 equals 0. And then we'd say I times 16 equals 6 minus 19.2 divided by 16 equals negative 0.825. So again, the purpose of source transformations, or mesh current, no voltage, don't go away. They're still so useful for us. They're so handy. But source transformations are handy too. So source transformations allowed us to take this circuit, which would have been, this circuit would have been 3 mesh equations, solving 3 simultaneous equations. And we were able to, just with a couple little swaps back and forth, we were able to reduce this down to one single loop. So that's pretty powerful. That's pretty useful. But again, this was only useful in this circuit. What if I'd done all these source transformations and then I say, okay, what's the current through the 5 ohm resistor? No clue. We have to unravel this whole thing. So if you're facing a situation where you're asked, all these details about all these different parts of the circuit, just go ahead and do a mesh current or a node voltage. But if you're only asked about one little piece of a circuit, then this technique of source transformations can be very helpful. What's some other stuff that can show up when doing source transformations? Some other stuff that can show up is things like this. Anything in parallel with a voltage supply is just the voltage supply. Why is that? Well, let's go back to what we mean when we say source transformations. A source transformation is saying this voltage supply in series with a resistor is equivalent to this current supply in parallel with a resistor from the perspective of the rest of the circuit. Source transformations are always the rest of the circuit doesn't feel a difference between this current supply in parallel with this resistor or this voltage supply in series with this resistor. It's always about what does the rest of the circuit feel. And in the case of a voltage supply maintains the voltage across its terminals. And with respect to those terminals, the rest of the circuit doesn't know anything other than the fact that there's Vs volts between those terminals. So if I'm, ignoring all of this for a sec, the whole rest of the circuit here, all it knows is that there's Vs volts here. Whether or not there's a million resistors here, the rest of the circuit doesn't feel it. The rest of the circuit only feels that Vs volts between those terminals. So anything you put in parallel with a voltage supply, it still matters, right? It's still burning current. It's still burning power. So, it's not like putting things in parallel with a voltage supply doesn't mean they exist. It just means they don't impact the rest of the circuit. So whenever you have something in parallel with a voltage supply, you can get rid of it for the purposes of simplifying the rest of the circuit. Now, again, if you're looking for, if you were looking for the current through RP, well, obviously that's easy to find, but you wouldn't want to get rid of it for simplification purposes. But if you don't care about RP, what do the young people say? You got to yeet that thing, or is it yeet? Is it? Boy, I hope that's not inappropriate. If it's inappropriate, I'm too tired to go back and edit this video. So hopefully yeet is one of those that's acceptable. I'm sure you'll tell me if it's not. Someone will. All right. So, So put something in parallel with a voltage supply, get rid of it. Don't care. Same thing with current supplies. If something's, if you got a current supply is going to keep whatever current is set by that supply, that will be the current flowing through it. So if you want to toss things in series with the supply, it doesn't matter. If you want to toss resistors in series with the current supply, and make the current supply work harder, okay, it's fine. Current supply doesn't care. But the rest of the circuit also, well, the current supply might care, but I mean, the rest of the circuit doesn't feel the difference. Things in series with the current supply, you don't know. Again, put this in a black box. You don't know what's going on in here. As far as the rest of the circuit's concerned, there's IS amps flowing here. It doesn't care if there's a resistor here. It doesn't care what's in series. You could have a voltage supply here. I don't know what I'm doing. You could have anything you want in series with that current supply, except for another current supply with a different magnitude or a different direction. You could have anything in series with that current supply, and it doesn't matter. The rest of the circuit doesn't feel it. So anything in series with a current supply, we can replace with just that current supply. And again, though, for source transformations, we care about resistors in series with voltage supplies and resistors in parallel with current supplies. The case of resistors in parallel with voltage supplies or resistors in series with current supplies, those aren't interesting because those don't change, those don't impact the rest of the circuit. So if you do see that show up, just ignore it or take it out as a simplification step. All right, find the power developed. Let's do an example. Find the power developed by the 250 volt source. So again, the 250 volt source is what I care about. I'm gonna try to find this current flowing through the 250 volt source. That's the way to find the power. So I am going to leave that 250 volt source alone for now. I am going to leave it alone. I'm not going to transform it away. I'm going to leave it untouched, and I'm going to start on the other side of the circuit here. So I'm going to start over here. So let's start working our way through this circuit. So I do right now have some resistors I can combine. Yeah, don't worry about VO. I don't know why VO is labeled here. Ignore that. Forget about that. So I can combine these resistors here. So I got a 5 in series with a 15. And then I've got, and then that equivalent 20 here. That equivalent 20 is in parallel with this 100. So I have 20 in parallel with 100. All right. $16.6 repeating, lovely. Let's go ahead and redraw this circuit. Usually on a quiz or a test, I'll tell you to redraw the circuit at sort of major intermediate points. So, you know, we combined all the resistors we could. We showed our math for combining them, and we'd redraw the circuit. Okay. And what about transformation? Well, we don't actually have a current supply in parallel with the resistor right now. We have a current supply in series with a 10. But what did we just talk about? When you got a current supply in series with anything, yeet that sucker, right? That better not be inappropriate. I'm gonna have to Urban Dictionary yeet now. Okay, so get rid of it. 8 amp current supply. Now we got an 8 amp. Now we got a current supply in parallel with the resistor. So now we can do a simplification. And one thing to note though is this current supply was pointed down, which means my voltage supply, when I combine this, is going to have the positive on the bottom. So we're going to want to be very careful with that when we do that. So, oops, okay. So this equivalent voltage, the equivalent voltage is going to be 8 times 16.6. That's going to be $133 repeating. So let's just did I leave myself? No, I didn't leave myself another space. All right, that's fine. We have an eraser. So again though, the thing I want to be careful about, and I'm just draw this really quick, is I had a current supply pointed down. in parallel with a resistor. That's going to have to convert to a voltage supply oriented like that in series with a resistor. So we got to be very careful with that. So we had 16.6 and we had 133.3 repeating. Okay. And now, now that 16.6 is in series with the 25, so we can just combine that to I should have shown my math here. 16.6 plus 25 equals 41.6. So this is a 41.6 repeating resistor. And let's do another source transformation. So let's clean up some of this. My magic eraser here. And now, once again, now remember, we got a voltage supply positive oriented down, so the current supply is going to have to be pointed down when we replace it. But now we have 133.3 divided by 41.6. That's going to equal 3.2. So 3.2 amps in parallel with a 41.6. But again, it's got to be pointed down. Okay. You know, and again, this is simple enough that I could probably, you know, be close to doing a source transfer. I could be close to finding this current right now. But obviously let's combine these in parallel. So we have 41.6 in parallel with 125. It's 31.25. Ugh. Okay. And now, if I'm trying to find this current, I'd probably just solve it now. So this current I, it's going to be, by Kirchhoff's current law, it's going to be this current plus this current. So it's going to be, I is going to equal 250 divided by 31.25 plus 3.2 amps. That's 8. So there's 8 flowing down here. And 8 plus 3.2. to 11.2 amps. So the power, if this was our current I, that was current flowing out of the positive terminal. So making myself some space on this page, I didn't leave myself enough space on. So power here, because our labeled current is flowing out of the positive terminal, power is going to be negative I times V. That's going to be negative 11.2 times 250. It's going to be negative 2,800 watts, which is, so negative 2,800 watts, which is 2,800 watts developed. So that's the magic of source transformations. And that's what we can do with them. And notice we encountered a little squirreliness with that resistor that didn't matter. Did it really not matter? Well, it matters to somebody. It matters to the current supply. The current supply had to produce, an extra voltage across its terminals to maintain that 8 amps of current. That 10 ohm resistor matters in terms of the total power dissipated by the circuit, but it doesn't matter as far as the 250 volt supply is concerned. The current through the 250 volt supply, the power delivered by the 250 volt supply, that is not at all impacted by that 10 ohm resistor. So when we were simplifying when we were reducing the remainder of the circuit with respect to that 250 volt supply, we were able to just get rid of it. Okay, so sort of taking this to its extreme, it turns out that anytime we have any circuit of any complexity, as long as it contains resistors, voltage supplies, current supplies, dependent supplies, independent supplies, doesn't matter. Any circuit that's composed of these elements can be reduced down to a single equivalent voltage source in series with the resistor, or a single equivalent current supply in parallel with the resistor. And when we take our big, giant, complicated circuit and we reduce it down to that shape, that is called the Thevenin or Norton equivalent circuit. And it should also be noticed that Mr. Thevenin had a little dash over the first E in his name. I think Thevenin, I don't know. I spent about 10 seconds looking for the character that's the E with the line over it, and then I gave up. That's how. There's so many of these slides to put together. So just know there should be a dash. I could have found it in the time I spent talking about it, but I don't. Maybe one of you knows what that E with the dash over it, what that hyphen's called. I'm not a botanist, right? I don't study these things. So when do we want them? So why would we do that? We have this big complicated circuit and we reduce it down to just a voltage supply and a resistor. Why would we want to do that? We want to do that because quite often we have a big complicated circuit. We didn't want it to be big and complicated. It is because of the way it's structured, right? We didn't have a choice. Usually these circuits are not actually, you don't actually have a bunch of current supplies and a bunch of voltage supplies and resistors. What you have is you have electronics that behave like those supplies, and so you're analyzing them like that. And a lot of times these are components that you didn't mean to have there, right? What's shown as a voltage supply was actually an unintended voltage that was produced by something, and what's shown as a resistor was an unwanted resistance that was produced by something. But you end up having these fairly complicated circuits. And quite often, you don't necessarily care about the details of all of it. All you care about is, what is the circuit doing to something that's connected to its terminals? So let's say your circuit is a power supply, and it's got all these unwanted resistances or non-ideal resistances, and it's got all these amplifiers that are in the process that are used to convert the current. And you're finding the equivalent of those with these dependent sources. And really, though, what you care about with this supply is with this, let's say it's a computer power supply. You care about what happens when you connect a load to its terminals. You don't necessarily care about the details of what's going on inside. You want to know what happens when you connect something to it. Or let's say you have an amplifier circuit for a radio and you want to connect it to an antenna. Well, you don't necessarily care about the details of what's going on in the radio circuit. You want to know what it's going to do to the antenna. What happens when you connect the antenna to it? What does the circuit do to this thing you're connecting to it? And that's where Thevenin and Norton equivalents really are important. And they allow us to take a complicated circuit and just say, relative to two terminals somewhere in this circuit, And these are usually two terminals that you imagine kind of escaping a black box. These are the two terminals that are sticking out that you connect things to. Right? You plug an antenna into it, you connect a resistor to it, you plug a light bulb into it, whatever. Relative to those two terminals, what does our circuit do? How does it behave relative to these two terminals? And once again, I always like to consider this sort of black box equivalent. Right? So let's say we have some big circuit here. Got a voltage supply, it's got a resistor, it's got maybe a current supply here. It's got another resistor, voltage supply, whatever. We got something going off here. I don't know what's going on, right? And you got all this stuff here, but you don't care, right? You just want to know what do these two terminals feel like? If I'm something that's connected to these terminals, what do I feel is inside this black box? I don't care about the details. I don't want to know the details. I'm looking for the simplest equation I can that represents the stuff that's inside this black box. Well, that's where Thevenin and Norton come in. And, I always like to think, if let's say I want to take all of this junk that's inside this box here and I just want to replace it with something like this, again, I have this question of, well, what if I shorted the terminals? If I short these terminals AB, what current do I see here? Well, if this had been a voltage supply in series with a resistor, then this current would be the voltage supply divided by the resistance. And when it comes to Thevenin and Norton equivalent circuits, we give specific names to these. So for the Thevenin circuit, which is a circuit reduced down to a single voltage supply in series with a single resistor, we call that the Thevenin supply, the Thevenin voltage, and we call it the Thevenin resistance. And the Norton supply, to clean this mess up a little, the Norton supply, you can imagine, is just this. And that's the Norton current. And the resistance is in parallel to, oddly enough, we tend to also call that the Thevenin resistance. So the Norton equivalent circuit is just the current supply in parallel with the resistor version of the Thevenin equivalent, which is the voltage supply in series with the resistor. So you can probably imagine that the Norton current equals it equals the voltage supply divided by RTH. And again, it's pretty obvious why RTH is RTH here, because we just talked about source transformations. But finding these, we could always find the Thevenin and Norton equivalent to a circuit by just doing a bunch of source transformations. That is always an option. But usually we don't want to necessarily do that. We'd rather find it quicker than that. We'd rather not have to go through all those steps. And sometimes what's easiest is to just do the tests that we've talked about. What happens if you short the terminals? Like, let's say we have committed to the fact that we have some complicated circuit inside this black box. And we have committed to the fact that whatever this complicated circuit is, it can be represented as a voltage supply in series with a resistor. Our question then is, how do we determine what this voltage value is and what this resistor value is? Or if we've determined it can be represented by a current supply in parallel with a resistor, how do we determine that current supply value? And how do we determine the resistor value? Well, let's think about the tests we could do. If we were to assume that this is the structure inside of our black box, and we shorted these terminals, we connected a wire between these terminals, we could say, what is this current flow? So this, if you short these terminals AB and you measure the current, that's called the short circuit current. And it's fairly obvious from this circuit that the short circuit current is going to be the Thevenin equivalent voltage divided by the resistance. That's just simple Ohm's law. You could also say, what if you left these open? What if leaving these terminals open, what if you measured this voltage? Typically, we call that the open circuit voltage. And what do you think that is? If you measured this voltage, if you left the terminals AB open, what would this open circuit voltage be equivalent to? It's going to be equivalent to VTH. Why? Well, because one of the features of leaving these terminals open circuit is, if these are open circuit, what's the current flow here? 0. We have no current flow here. And if there's no current flow, then what's the voltage across this resistor? Also 0. So if we have no current flow through a resistor, we got no voltage across it. So basically, if we have VTH volts here, and we have no voltage drop across the resistor, we've got to have VTH volts drop by Kirchhoff's voltage law. We have to have VTH volts dropped across these terminals AB. So the open circuit voltage will be equal to VTH. So these are the two tests we can do. We can say, however complicated my circuit is, if I shorted the terminals and measured the current, that's going to give me this relationship. And if I left the terminals open and I measured the voltage, that's going to tell me the Thevenin resistance. And knowing these, so if I know the short circuit and I know the Thevenin voltage, then I can calculate RTH. I can calculate the Thevenin resistance. And not only can we do this in real life, if we actually had a circuit with two terminals sticking out and mystery inside, if we actually had a black box, we could do this. We can also do this when it comes to the circuit. We could take any complicated circuit and we could short these two terminals and calculate the current flow through it based using whatever techniques we want. And we could leave the terminals open and we can measure the voltage across it using whatever techniques we want. And that's totally okay. So let's do it. So I'm going to go through one example, and then I've been talking for too long. You don't want to hear me talk anymore. We'll give this lecture a rest. But let's do it using the techniques that we talked about. So first of all, let's take this circuit, and let's say if we're trying to find the Thevenin equivalent, and again, we want to just pretend that all of this is inside of a black box. So the first thing we're going to find is this open circuit voltage. So leaving these terminals AB open, so no wire between them, no resistor between them, just leaving them open, finding this voltage. Well, based on the structure of this circuit, what do we know? If we leave these terminals open, how much current is flowing through this resistor? No current. There can't be, the open terminals means there's nowhere for current to flow. You can't have current flow through that 4 ohm resistor. And if there's no current flow through the 4 ohm resistor, there's 0 volts across it. And if there's 0 volts dropped across this resistor, then that means that this voltage here is going to be the same as this voltage here. Hopefully everybody sees that. That because we leave the terminals open, and that means there's no current flow through the 4 ohm, the 4 ohm resistor is basically there's no current through it, there's no voltage across it, it's not really participating in the circuit right now. It's still there, and it's still going to matter when we short the terminals, but for now, for the open circuit case, it's not doing anything. So finding the open circuit voltage across the terminals now becomes a matter of finding this voltage here. And we don't care about this resistor. So let's do that. Let's find that voltage there. So let's redraw this circuit. And again, my question is, what's this voltage here relative to down here? Okay, well, if I'm trying to find this voltage, I'm just going to use node voltage really quick. Pick a reference, call this V1. Just going to write V1 minus 25 divided by 5 plus V1 over 20 plus negative 3 equals 0. You know me, multiply this thing through by 20. So multiplying it through by 20, we get 4V1 minus 100 plus V1 plus negative 60 equals 0. So then we have 5V1 equals 160 divided by 5. 32. Okay, so V1 equals 32. And V1, again, this voltage here is my open circuit voltage. So VOC, my open circuit voltage is 32. And VOC equals my Thevenin equivalent voltage. So again, going back here, if we left these terminals open and we measured the voltage, that is our Thevenin equivalent voltage. So we found the Thevenin equivalent voltage. It was 32 volts. All right, that's part of it, right? Now that's part of it. But now we also need to find RTH. And the way we're going to find RTH then is using this equivalent here. And that is to say, if we short the terminals, if we connect a wire between the terminals now, we connect a wire here and we measure the current flow through here, that current is going to equal our Thevenin voltage divided by RTH. And we've already solved for the Thevenin voltage. So if we solve for the short circuit current, it will give us a way to find the Thevenin equivalent resistance. So let's do that. Let's now short these terminals. And shorting these terminals, and again, my question now is, what's this current? This is the short circuit current. So now I got to find the current flowing through it. Now in this case, this current is the current through the 4 ohm resistor, right? The short circuit current is going to be the current flow here. How am I going to find that? Well, I could do mesh current, but I kind of want to do node voltage again. It's just going to be one equation, but it's going to be a different equation. That's the key. I can analyze the open circuit case and the short circuit case are two different circuits. And so if I want to use a technique, I can't recycle the math I already did. I have to redo the math from scratch. So we can do another node voltage problem. That's fine. But it's going to be a different equation. So let's do it. Let's do another node voltage to eventually find this current. So we'll call this V. We'll call this our reference. So now our math is going to be V minus 25 divided by 5 plus V over 20 plus -3 plus, here's the part that's different, V divided by 4 equals 0. Again, I can multiply this thing through by 20 though. Multiplying it through by 20, I get 4V minus 100 plus V plus -60 plus 5V equals 0. So now I have 10V equals 160. So now I have V equals 16. This is the part that kind of confuses students. Students say, well, wait, we just solved V and it was 32. Now we solve for V and it's 16. Well, remember, this is a different circuit, totally different circuit. Now we shorted the terminals now. So of course, you put a wire between two terminals, you're going to mess with your circuit. That's what we just did. So we put a wire here. And now we found, and again though, this is a different voltage now. Now we're not solving for the voltage across the terminals. We had just solved for the voltage of this node, which actually is not even accessible by the terminals AB. We're not done yet. We still have to find this current here. So the short circuit current in this case, the short circuit current is the current through the 4 ohm resistor. So that current's going to be V over 4 ohms, right? We actually had already written the short circuit current over here. So V over 4 ohms, 16 divided by 4, that is going to be 4 amps. So our short circuit current is 4 amps. And going back, our open circuit voltage was 32 volts. Oops. So if I short circuit equals VTH over RTH, then we can say that 4 amps equals our Thevenin equivalent voltage was 32 volts divided by RTH. So we can say RTH equals 32 divided by 4, which is equal to 8 ohms. So what does that mean? Big picture. We can redraw this entire circuit. We could redraw this entire circuit. Maybe here. Let's clean up some space here. This entire circuit here could be redrawn as a 32 volt supply in series with an 8 ohm resistor. And what if we wanted to find the Norton equivalent? The Norton equivalent, well, it's just going to be 32 divided by 8. So the Norton equivalent, and I'm just putting this wherever I want. The Norton equivalent would be 32 divided by 8. That's going to be 4 amps in parallel with an 8 ohm resistor. So this is our Norton equivalent. This is our Thevenin equivalent. And it should be noted that that 4 amps, our short circuit current, that is the Norton current. So the short circuit current is the Norton current. The open circuit voltage is the Thevenin equivalent voltage. Very handy. Okay. There's another way we can find our equivalent. So we can always find the equivalent resistance, the Thevenin equivalent resistance of our circuit, by finding the short circuit current and finding the open circuit voltage. But there is another trick that we can use to find it. And that is, we can set all of our sources to 0 and solve for the equivalent resistance with respect to the two terminals. What does setting the sources to 0 mean? Well, setting the sources to 0 is something that always kind of trips students up. But just think about it. What is a 0-volt voltage supply? A 0-volt voltage supply is just a wire. So if we replace this with just a wire, that is setting our voltage supply to 0. We've generated a 0-volt voltage supply with a wire. What's a 0-amp current supply? A current supply that maintains 0 amps between its terminal, that's a broken wire, right? That's an open circuit. So we can replace this with just an open circuit. So if we redraw this circuit as a 4 ohm resistor, leave this open, and a 20, and a 5, and we say, all right, from the perspective of these terminals A, B, what's this resistance? What resistance do these terminals A, B, C between them when all of our supplies are set to 0 in our circuit? Well, because this is not here, from the perspective of these terminals A, B, we have a 5 in parallel with a 20, right? Which is 4 ohms, so we could replace this with a 4. And then we have a 4 in series with a 4. So we could do that. So that's it. That's REQ. We found that was actually really easy. And quite often, that's the easiest way to do it. So the shortcut to find REQ directly is to set all your sources to 0 and find the equivalent resistance with from the perspective of the terminals. What trips people up, though, is that from the perspective of the terminals. You have to say, what's the resistance from terminal A to terminal B? What's the resistance seen in that direction? And that's sometimes where the challenge lies. But now finding equivalent resistance we can't just find that. Anytime we want to find the Thevenin and Norton equivalent, if we use the shortcut to find the equivalent resistance, that's fine. But we also are going to have to find either the open circuit voltage or the short circuit current. It's up to us, though, usually. So it's kind of just a matter of which one do we think is going to be easier to solve. In this case, my circuit to find the short circuit current was a little bit more complex than my circuit to find the open circuit voltage. So I probably, in this case, would have chosen to find the open circuit voltage and then used the technique to find the equivalent resistance. But, it's really up to us. So you have to find the short circuit current, the open circuit voltage, the equivalent resistance. You get to pick 2 of those 3. It's up to you, your choice. Pick two of those 3, find 2 of those 3, you can find your Thevenin and Norton equivalent circuit. So next time we are going to expand on Thevenin and Norton equivalents. We are going to talk about, we haven't talked about dependent supplies with Thevenin and Norton equivalents, and this is where it gets a little tricky. So using dependent supplies with Thevenin and Norton equivalents, that's where we start to have to do some weird things that's where we have to start to treat them as special. We are going to then also talk about superposition, the superposition technique, and then we are done with chapter 4 after that. So one more video to get through, and then the last video is part F. So we have chapter 4 is a biggie, and once that's done, we are just blue skies out of chapter 4. So I will see you next time.